because at starting the vehicle is at rest, you have to overcome the static friction, so you need more effort, more torque. And as the vehicle keeps rolling or keeps moving, there is rolling friction which is significantly less in comparison to static friction. So thereby, as the speed increases, smaller torque will do the job. Right? So this is the typical torque speed characteristic that is desirable in an electric vehicle, that we have to get, right? So this is what is achieved with the gear arrangement that we have in the conventional IC engine vehicles. First gear gives higher torque, and as the higher speed you reduce the gear, which will actually give me low torque and high speed. Okay, so this is the torque speed profile I should achieve with the electrical motor, right? So if the motor itself can give this kind of torque speed profile, then I can directly put that motor with no control, I can operate it. But the issue is there is no electrical machine that is available that exactly has this kind of characteristic. So then how to deal with the things? So what we do is we control the motor in closed loop in such a fashion such that we forcefully make the motor to go according to this characteristic as per my requirement. Whatever reference I give, I will ensure that with closed loop control, that much torque is produced at that speed, right? So like that, I must be able to do that, right? So we have to do some control to achieve the desirable torque speed characteristic. No motor fits exactly the torque speed characteristic. And other consideration, first thing comes cost, right? Whichever is cheaper become more commercially viable. And any other consideration, power density and weight. Why these are important? Because in an electric vehicle, you have to carry the motor along with the vehicle. So if for a given power rating motor, the power density is high and the weight of the motor is small, so for the same power rating, you can carry more passengers or more luggage. So that's why will have advantage in the electric vehicle, since you have to carry the motor along with you. If the motor weight itself becomes high, then you will have less scope for the luggage or more passengers. So that is why you need a power density high and weight less, as much low weight motor as possible. And then you also need to consider what is the maximum achievable torque or speed, or the top speed of the vehicle, because this is important for commercializing the EV. If a EV I make with only 40 kmph top speed, then it cannot be used for uh, highways, right? So you have to see that at least reasonable maximum speed or torque is achievable by the vehicle, so that you can use it for all purposes, right? So then maximum achievable torque. This is also important because this is also for advertising the vehicle. 0 to 100 kmph, how fast it can achieve, that depends on maximum torque. Not only that, as I have mentioned, you have to forcefully make the vehicle to follow this torque speed characteristic. So initially you need a high torque. If this high torque, if the motor itself can deliver this high torque, I can eliminate the gearbox. If I eliminate gearbox, what advantage I get is I have higher efficiency, because gearbox also has some power loss. You will have to put more effort or more power to get the same power output from the vehicle. Instead, if there is no gearbox, your power directly goes on to the motor, so or the wheels, and so you can save some losses. So that's why if the top torque achievable by the motor is sufficient to start the vehicle, then you can remove the gearbox and increase the efficiency of the drive. Right? So these are the factors you have to consider for choosing an electrical machine for EV application. And of course, ease of control. This is not directly related with the application, but from the manufacturer point of view, if a motor or an electrical machine is easy to control, it requires lesser effort in the control algorithm design, and thereby less amount of code is required in the microcontroller. So a cheaper microcontroller can do the closed loop control. Instead, if the algorithms become complex, then you need a heavy controller and lot of code is to be written there. And as you know, more complexity introduces more chance of errors. So which will be less if it is easy to control. And then now we have to select based on the available. If we see, first comes squirrel cage induction machine. These are the predominantly used motors for many applications. So what if we consider squirrel cage induction machine, which which features satisfy and which doesn't satisfy? First thing is torque speed characteristic, it doesn't match. No motor matches, as I told you. Cost wise, it will be an advantage if I go for induction motors. Squirrel cage induction motors. They are cheap and rugged. So cost, I have an advantage. Power density and weight, we do not have so much advantage. They are not very power density, high power density motors, and weight also significantly high, but not as high as DC motors. So it is medium. So this is not directly an advantage, but it is moderate. Maximum achievable torque or speed, there is a maximum torque achievable by a given induction motor. So this can be taken care of. Ease of control, again, I have a disadvantage for the induction motor because they are singly fed motors, squirrel cage induction machines. So you have a bit complicated control algorithm to write when you go for squirrel cage induction machine. So this is a negative point, and this is moderate, this is okay, and cost wise it is very good. So this way squirrel cage induction machines, if I choose, you have some good, some bad. Brushless DC machines, if I go for, the cost, I have a drawback. They are costly because of permanent magnet. They are costly. Power density, weight, I have good because they are having high power density and very low weight for the given power rating. Maximum achievable stock or speed, this is also possible. Ease of control also moderate, not as complex as induction machine. So you have cost disadvantage, but other moderate or advantage if I go for brushless DC machines. And then permanent magnet synchronous machine, those are also having same features like brushless DC machine. Cost, it is higher. Power density, weight, it is lower, and other moderate. Switched reluctance machines, these are coming up in the recent future. Cost wise, they have an advantage, and if commercially produced, these will be the cheapest among all four cost wise. And power density and weight, it is moderate. It is not it is better than induction machine, but not better than BLDC or permanent magnet machines. Maximum achievable torque or speed, this is also very high advantages they have. Ease of control is also moderate. So switch reluctance motor also has a good opportunity. And then etc. written because many manufacturers or many researchers are trying to manufacture customized machines for EV applications, which has maximum of the desirable characteristics as we discussed, right? So by making use of the low cost nature of induction machine, high power density nature of brushless machines, whether I can combine and make cost moderate and medium complexity control algorithm like that, right? So these are customized machines, but we should understand that if you go for available machines, they are very easy to commercialize because manufacturers have been making these machine or available machines at different ratings, so you can buy and then put it in your EV. Whereas if you want to customize an electrical machine, then you have to manufacture the machine as well, right? So that becomes an additional effort required there, right? So we have an advantage if we go for magnetless electrical machines like squirrel cage or switched reluctance machine. What is the advantage is, first thing is cheap, because ultimately any commercialization comes with the cost advantage, and these machines have cost advantage. Rest everything we can manage, but cost is the primary factor always when we try to commercialize something. And ease of mass production, it is possible. And vehicle cost cannot be dictated by, because India we are not having permanent magnet reserves, so we have to import the permanent magnet. So then it will be dictated from where we are importing. So that's why we do not have direct control over the vehicle cost the moment we are using permanent magnets in the EVs, or we are using electrical machines that have permanent magnet inside. So it is always preferable to go for available options which do not have permanent magnet, like induction machine and switch reluctance machine. Right? So now we will discuss induction motor for electrical vehicles. So if I want to use induction motor for electric vehicles, now I have made a choice, and then we have to next see how to choose the control algorithm for EV application, and which control algorithm is how much complex, and what advantage disadvantage that will give. For understanding that, first we'll see the per phase equivalent circuit of a three-phase induction motor. That looks like this. This is one phase. So other two phases also same. Only difference is the phase voltage will be A phase, B phase, C phase. Only voltage will be different. Equivalent circuit remains same. This is a balanced induction motor, I am assuming. Right? So in this, if you observe, I have RM, JHM. These are the magnetizing branch resistance and inductance, and R1, R2 are the resistances of the winding, JH1, JH2 are the leakage inductances, and this is the air gap power, from which if I remove the rotor copper loss, it will be the output power. Okay. So this is the basic equivalent circuit of a three-phase induction motor. In this basic issue, when I am trying to control is, I have only EG or the voltage in my hand that will come from the converter. By changing the voltage, I must be able to control the output power, which is basically coming from the R2 by S component. So now whenever I change the voltage EG, I naught as well as I1, both will change. And the problem is inductors here. An inductor property is which does not allow sudden change in current. So what happens is, when I change this voltage some value to, if I increase EG, then the current flowing IP will not change immediately, because this inductors JH1, JH2 here and JHM here oppose sudden change in current. So this current IP will take long time to change, and until it changes, the output current I1, which is going to R2 by S, will not change. And why it has to change? This I1 current actually represents how much output power or how much output torque I am going to give on the vehicle, on the motor. So what happens is, whenever I change voltage to suddenly brake or accelerate, the actual acceleration takes place after a delay. Who is causing the delay? These inductors, JH1, JH2 and JH7, because they doesn't allow sudden change in current. Among these inductors, these JH1, JH2 are very small inductors of the order of millihenry, maximum 10 power minus 2 Henry. These are leakage inductances, very small. Whereas this is a very large inductance, which is the magnetizing inductance. So this inductance, if I try to approximate, this inductance is the affecting one, which is stopping the machine to respond quickly because it is not allowing sudden change in I0. If I0 doesn't change, I1 cannot change and IP cannot change. Even though voltage has changed immediately. Voltage I can change instantaneously using converters, but current will not change immediately. So what I should be doing is, I should somehow affect allow that, make sure that this inductor do not come in the change of I1 current. So for that, what we do is we generally try to maintain I naught constant. As long as I naught is constant, this inductor is not disturbed, so its uh, inductance will not come into the change of I1. So how do we do that? First control technique is V by F control, where what we are doing is voltage by frequency. If I maintain constant, the current in JHM is actually V by JHM, which is omega LM. Omega is the frequency. So V by omega, if I keep constant and change EG, then the current in JHM is always constant as long as V by F is constant. So that is what is V by F control. In this, approximately we are trying to make the current in the bigger inductor constant, but still change the voltage. Voltage, frequency together, if I change, this current will remain constant. So what is the advantage I am going to get? Advantage is if this current remains constant, this current can change quickly. If I change to another V by F, this current will change quickly. This current changes quickly, IP can change quickly, and the output torque can change quickly. When the output torque changes quickly, you can see a faster response on the motor. You have applied brake, you have changed the voltage making V by F constant, then you can see that the motor stops very quickly. So that is V by F control, that we have one control technique. And then there is direct torque control. Actually, in every control technique, we actually try to maintain this current constant ultimately. So whenever I try to maintain I naught constant and change I1 somehow, then I1 can change quickly. Okay, but we are applying, everything has to happen through EG only. Right? So what is these controls we see, and then there is vector control also. So these three techniques are predominantly used for induction motors. So we'll briefly see one after the other. V by F control, as I told, V and F we change such that V by F remains constant. And then we give that voltage with frequency to the inverter, which actually gives a voltage with variable frequency according to V by F constant to the motor. And then I will design my control algorithm. Here you can see for any speed reference I give, actual speed I am checking, and then trying to get some slip with which I add the speed to get the frequency. And when I have the frequency, for the given frequency, since V by F2 should remain constant, so corresponding voltage I can get from the graph. At starting, you need to give a little higher voltage. These are for the non-idealities. Because in starting, frequency is zero, so zero voltage I cannot give because there is a resistance which we are ignoring. So that's why some boost in voltage, and you cannot go beyond rated voltage as well. So these two are the limitations of V by F control. At starting, you have to compensate for the stator resistance drop, and after rated voltage, you cannot still increase the voltage because rated voltage means that is the maximum voltage capacity of the motor. You cannot give more voltage to the motor, right? So that these two limitations, but within the range, you can make V by F constant and apply on the motor through an inverter, which will help you in making a fast response in the induction motor. And then this is the typical torque curve. Till rated, I maintain V by F constant, so I can actually achieve constant torque. Okay, and then I cannot maintain voltage constant. Voltage keeping at rated, frequency only I can increase beyond rated. So there you get the constant power mode. Okay. And then voltage, how I am changing, some voltage boost at the starting to compensate for the series resistance, and then V by F constant until rated. After rated only, I will see that V will not increase further, only F will increase if you want to operate beyond rated frequency. So that is about the VBF control. Drawbacks I told you, you cannot go beyond rated, and starting you need to give some voltage boost for the stator resistance compensation. Then direct torque control. So as the name change the stator flux in this direction and also increase the torque. So I should choose V3. Like that, if I want to decrease, I should choose a vector which is in opposite direction. If I want to move the is in the backward, in the clockwise direction. So if I choose V6, then it will come back, right? Not only it will come back, it will reduce gamma, so it will change the torque, it will reduce the torque, right? So if I want to increase is but reduce the torque, then also I can manage. So I choose a different vector simply here. Suppose V2 I choose. V2 if I choose, V2 if I choose, then psi s magnitude will increase, but gamma will decrease. So if gamma decrease, then torque will decrease, but flux will increase, right? So like that, by choosing a different space vector, I can get every possible combination of increasing or decreasing flux as well as increasing or decreasing torque, right? So independently I can achieve increased torque, decreased flux, or increased torque, increased flux, or decreased torque, decreased flux, or the other. So all four combinations I can achieve by choosing a suitable voltage vector from the space vectors. So these all voltage vectors I will make a table and store in the memory. And then based on the flux and torque errors, I will apply suitable voltage vector which will do the job for me. Suppose I want flux to increase, torque to increase, and current portion of flux is somewhere, I will choose one vector. And then that will do both the requirement. Same way, I will do that for every instant of time and using this table and my requirement, right? So this is the switching table which will be kept in the memory, and then I am trying to control the torque directly. Directly means directly I am applying a voltage based on the torque error and flux error, right? So here also flux we try to keep within a certain band and will not allow it to change beyond, so that we get fast response on the motor, right? So whatever voltage vector is selected finally, that has to be applied using the three-phase inverter and the motor it is given to. Okay. And for feedback, you have to estimate the flux as well as the torque, so that you know the error, and based on the error, we take the corrective action used by choosing a suitable voltage vector in the direct torque control. So this is the table given for different. One means it is error is positive, minus one means error is negative. Zero means error is zero. Okay. So this way we make a table and then feed into the controller, which will apply that particular voltage according to the flux and torque errors. Okay. So that is about direct torque control. It has a better response in comparison to V by F, but still we are ignoring ISRS drop, which will become a problem in the low speed operation, because low speed means low current, and this drop will become, and low voltage. So low speed low voltage means this voltage becomes almost comparable to ISRS drop. Then I can no longer ignore this ISRS drop, and until I ignore, I cannot write this equation. So that is the problem. So at low speeds we have an issue with the DTC, otherwise at high speed this works well. So then came induction motor vector control. In this, actually, we try to go to the flux vector and make it constant. And in the uh, rotor flux orientation, if I do, ISD star is nothing but the flux reference directly. So flux I am controlling in the D axis, and then torque I am controlling in the Q axis, so that I will always have a high fast response control in the induction motor, and at the same time I am able to control at low speeds as well, because when flux I am directly trying to control, there is no approximation I am trying to do. Flux I am measuring feedback, and then I will keep a reference, and luckily in the rotor flux reference frame, I get flux is proportional to ISD, direct related. So I can give ISD reference instead of flux reference here, right? So I sense the speed and feedback, and then I do some closed loop control. But for this indirect vector control, you have to go to two phase and also two phase rotating reference frame, which involves higher computations. So complexity will increase of the system, but this will give a better performance even at low speeds. Okay, so in this again, if I am doing speed control or you are sensing the speed, you can remove the speed sensor further, because speed sensor or the mechanical sensors mainly are first thing to be create trouble in the system. Why? Because they are mechanically connected with the motor shaft as shown in this figure, and you have to take wire and signals from the sensor to the controller, and using this long wire you may have noise issues, as well as they may pick up noise or they may get distorted, and then based on that you have to work. And since you are taking with long cable, the voltages may not be accurate as at the point of the motor. So these all issues will come with mechanical sensors. So since only one mechanical sensor we are using, that is the speed sensor or speed encoder, so we want to remove that, then we have some advantages. Makes the motor less robust. In a noisy environments, it becomes tricky to get this data accurately. If I put a filter, then filter gives delay. If I put a strong filter, higher delay. Higher delay means present speed it will give after some time. So then how to control it in real time? And of course, the sensors add price or cost to the system. So this is the problem. So to avoid this problem, we developed a estimation technique, speed estimation. We are estimating the speed based on voltages and currents, using which this speed is used for the closed loop control of the induction motor. So this speed, if from estimator, if I use, I no longer need a sensor or the encoder. So thereby, these all disadvantages can be overcome. So we proposed some algorithms from based on literature. There are some issues with the literature-based speed estimation techniques, like presence of integrator, so low speed operation becomes a trouble. Presence of differentiator, when there is noise, it gets amplified. Presence of differentiator and instability, this is also having noise problem. And there are some MRAS model reference adaptive system formulations from my lab, which are reactive power based MRAS. It has some stability issues. ANN based MRAS, it needs offline training. So this is the proposed X-based MRAS, with which if we estimate the speed, we get higher accuracy. At the same time, this can be applied at all speeds, including very low speed and zero speed operation. So for the experimental verification of the proposed algorithm, we made a hardware setup. This is a 4-quadrant chopper for controlling the DC motor armature current, so that torque, constant low torque can be applied on the vehicle or the motor running the vehicle. Voltage sensor, current sensor, and then this is an FPGA board with which hardware's coding is done, and the results are taken. It's a semicron three-phase inverter, speed encoder. So here speed encoder is just used to check with the speed of the actual motor and the estimated speed. So and compare whether they are equal or any deviation exists. This is the other view of the hardware setup. This is the motor rating available in the lab, 1.3 kilowatt, and then line voltage 400 volt. It is 1430 RPM, 4-pole motor, having the other parameters as given here. So this is the response for a speed reference of 0, positive 20 radian per second, negative 20 radian per second. and this is the reference is star, omega r is actual. And if I go for the second result, that is actual speed and estimated speed. So if you can observe, actual and estimated speed are almost same, right? So this third figure, psi rd, psi rq is actually showing the flux. Flux we are maintaining constant. So since we are maintaining flux constant, we are able to get fast response on the motor. This is a plus 20 minus 20 radian per second. So here the motor was running in clockwise, here anti-clockwise or in opposite direction. So like that, we give different speed references. This is a triangle speed reference, and as you can see, the actual speed is also trying to track the reference speed, and estimated speed also is accurately giving the estimate. And flux is again maintained constant throughout, so that I get fast response on the motor, and if this motor itself is used in an EV and ultimately the vehicle. Right? So the advantages is it is all stable, MRAs, flux estimation not required, low and zero speed operation we could do, and also reference model is free from machine parameters. No integrators or differentiators are used. So a disadvantage, a drawback of this algorithm is how to design proper PI controllers which are not sensitive to the MRAS. And it is also dependent on stator and rotor resistance. So if these parameters vary due to heating or other effects, then the estimation does suffer. So for that, we further proposed an active power and reactive power based this active power P, reactive power Q based MRAS with these structures to improve the MRAS further, speed estimation further. If you can see the features, there are no parameters involved in any of the equation. So, uh, and then if I try to see the stability of these proposed, PMRAS having unstable point, whereas Q1 is stable. So this Q1 is recommended to use for speed estimation, and there are no parameters involved in this. But there is tau RR involved in the omega slip equation. Therefore, ultimately rotor resistance will have an effect on this closed loop performance, but not any other parameter, even stator resistance. So the hardware result is similar in this case also when we are trying to estimate the speed using the modified QMRAS. And then we also varied the stator resistance by externally connecting a gang rheostat and then changing it. So even though we change the stator resistance, there is a small jerk, but it again restored back to the same reference speed. So thereby confirming that the proposed algorithm is independent of stator resistance variation. So this is an additional advantage we get in comparison to the previously discussed method. So independent of stator resistance. Other things remain same. So then still it is dependent on rotor resistance and sensitive to PI controller values. So this is the future work. So then till now we discussed vector control, direct torque control, V/F control, different control techniques for induction motor drives. Now we will try to see switched reluctance motor for EVs. And as I mentioned in the beginning, these are having lower cost even compared to induction motor. But if you try to buy now, they are seem to be costly because there are very few manufacturers for switch reluctance motors, so they have to specially make the motor for you. But cost wise or material wise, if we see, switch reluctance motor is supposed to be cheaper than induction motor. Okay, so what is a switched reluctance motor and what is its working principle? We'll see first. Switched reluctance motor has saliency. Saliency means non-uniform air gap in the stator as well as rotor. See, rotor also has perforation stator also has some projections, right? So the how this is operating, this is switched sequentially. Windings are placed only on the stator, say A dash, B dash, C dash. I place three windings from A to A dash, B to B dash, C to C dash. I can place its windings also for everyone, but that will again increase the converter configuration. So we two will put one winding. So three windings are required on the stator. Rotor, no windings. No windings on the rotor. And rotor is made of some magnetic material only. It is not permanent magnet, only a magnetic material like core of a transformer, right? So, and you have how to run this motor. So first, if I give energize A to A dash, A to A dash, I give positive voltage. Some current will flow from A to A dash in these windings that are wound, and when current flows, some magnetic field is established between A and A dash. Once magnetic field is established, this rotor, since it is made of a magnetic material, it will try to align itself according to A and A dash, choosing the least reluctance path. So the least reluctance path is now moving to A2 dash is this limb, so it will come very fast. So once it has the rotor has reached the right side position, then I can energize CC dash or BB dash. So which one should I select? If I select BB dash, the rotor will again move backward, or R1 dash will try to align now with respect to BB dash. So whichever is nearby projection of the rotor is R1 dash. So the rotor will move further clockwise, right? So if I want clockwise rotation, after A, B should be energized. Same way, if I want in anti-clockwise, instead of B, I will energize CC dash. Then R1 will try to align along C. When R1 align along C, I am able to get anti-clockwise rotation. So like that, based on the switching sequence, I can run the motor in clockwise or anti-clockwise direction. And how fast I switch from phases, that fast the rotor also try to align itself with the stator poles that are energized. Okay. So whenever I am trying to change the position of the rotor with respect to stator, the inductance will no longer remain constant. Why? Because this is a non-uniform air gap in this machine. So how the air gap and correspondingly the inductance gets affected. So when I reach the position where the rotor is aligned with stator, the air gap between stator and rotor in the between R2 and A in this figure, the air gap is minimum. So when air gap is minimum, the inductance, corresponding inductance will be maximum. And similarly, when R2 is completely out in the left side figure, the air gap is high. So when air gap is high or maximum air gap is there. So when air gap is high, I'll say that the inductance is minimum. And when R2 is trying to align with respect to the A, A phase, then the inductance is changing from minimum to maximum. When it has fully aligned, the inductance became maximum. So the per phase inductance profile of any phase of the switched reluctance motor will look something like this. As long as it is completely unaligned, it will be some L min, and when it is starting to align and going to align, the inductance will slowly rise until it is fully aligned. Once it is fully aligned, it will remain constant until the difference in the widths of these two. Then when then the rotor pole will go out of the alignment of the particular phase. So then the inductance drops, and then it remains zero until the next winding or next time a phase is energized. Then again same thing follows. Okay, so this will be the per phase inductance profile. So the difference is this top part is not there. It is going up and immediately coming down. What makes the difference? If the widths of rotor pole and stator pole are exactly the same, the moment it reached full maximum, it will again immediately try to de-align. So then you will have this kind of an inductance profile where it will immediately start dropping when after reaching peak of the inductance. Whereas if the width of stator pole or rotor pole is higher, then it will have some time where the maximum inductance will remain, and then it will start to de-align. Okay, so this is the combined inductance profile for a three-phase motor, and the below one is for a four-phase motor. So these are the equivalent circuit and equations of an SRM. Per phase, P, the applied voltage to the winding, suppose A phase winding, is the winding resistance into current IR drop for any wire plus the flux linkage d by dt. So the per phase flux linkage is given by L into I, where L is a function of theta, the position of the rotor with respect to the stator, and also current. Also current. So this is the net equation of the switch reluctance motor per phase, and this is the equivalent circuit. This is like back EMF. So now this is the linear SRM. If it is a non-linear SRM, the inductance will not go smoothly up and come down. It will try to saturate after some time and then come down. Right? It will not go till L max. Right? So it will saturate and some saturation. It will look more or less like this, not sharp. It will be something like this in a practical SRM with saturation. Right? So if suppose saturation for the timing, if we ignore, if the torque equation, if we see, it is dependent on I square dl by d theta by 2. What does this expression tell us is that whether you make positive current or negative current in SRM, torque will always remain positive. And torque is positive or negative is entirely dictated by dl by d theta, or the slope of the inductance with respect to theta. If this slope is positive, I am giving positive torque on the motor. If this slope is negative, I am giving negative torque on the motor. So again, if we go back to the inductance profile, where the slope is positive, theta 1 to theta 2. Here slope is positive. So here I can get positive torque. Here I can get negative torque. Negative torque region, positive torque region. And what about this part and this part? This part is zero torque region because slope is zero. So whatever current you send in the SRM in this position, you will only get zero torque. And here, if you send higher current, higher positive torque. If it is negative higher also, it will be positive torque only because torque is proportional to I square. So in this region, whatever you do, whatever current you send, you will always get a positive torque. In this region, whatever current you send, positive or negative, you will always get a negative torque. Right? This is a typical control diagram of an SRM. So when current is increasing, you give a gate pulse such that the current torque is there in the motor, and when it ended, I want to stop the motor also, because I am not going to get any torque in this region. This is zero torque region. And this is anyway negative torque region. If I want motoring in positive direction, I have to get the torque only during positive slope for every phase. This is for one phase. For other phase also, whenever that phase inductance become positive slope, you apply current. Okay? And then this negative torque is used in the regenerative mode. This is motoring, this is generating. Okay? So where you try to ensure current is there when this slope is negative. Same thing goes for other phases as well. So this is the control closed loop control block diagram of SRM, where we can observe that first thing is I need to know the position of the rotor. Based on that only I can apply the control signal, because inductance profile of every phase entirely depends on the position of the rotor. So when I know the position only, I can determine which phase is in the positive slope region, so that I can send some current in that phase and I will get a torque, ultimately a torque. So So first I have to get the theta. Once I get the theta, then what I should do? I should decide how much current I should send in the phase for a given torque. Right? So since torque is proportional to I square dl by d theta, so based on a given torque, I can decide how much current will give me this torque. Right? Because I should know where a current should be there, and I should also know at that period how much of current should be there, right? So that will be known from the torque to current conversion. Then this current I can give using hysteresis controller, which will try to keep the actual current within a certain band around this I reference. So that band we select based on the switching frequency available and other factors as well. So you decide. Once I decide, I know the theta, then you have to give the voltage to that particular phase, which is having positive slope region if you want to run in the motoring mode. If you want to run the motor in the regenerative mode, you have to use the negative slope region. Okay. So then we give the current in that particular phase, whichever is in the positive slope region, and then control the SRM. Right? So using an encoder, you always get the position of the rotor. Okay? So that way we always try to see at this instant which phase is having positive slope, and now I want to put as much current as required reference in that phase during that period, and another period another phase will come into play. So like that we'll be switching the phases A, B, C, D or A, C, D, B based on which direction of rotation you want, clockwise or anti-clockwise. So this technique which we discussed has some drawback. What is the drawback is when I am changing over from one phase to another phase, next phase, and the current profile. If you see this current profile, it has to suddenly rise from 0 to some IP and then again suddenly fall from IP to 0. Can any real motor winding follow this characteristic exactly? The answer is no. Why? Why? Because all windings are inductive in nature, which doesn't allow sudden change in current. So a practical SRM doesn't allow this type of sudden change in current. How the current will change? Current will change slowly until the reference is reached, and current will also not fall instantaneously like shown here. It will fall slowly in exponential or some other manner, but not instantaneously. So the problem is when I am want to have current or correspondingly torque in one position, I'm able to get that torque after some delay because the winding is not allowing sudden change in current. So the current is gradually increasing by some time constant based on the winding inductance and resistance. So due to this, what happens is the desired torque in the actual overall machine is not met until the delay is completed. So this comes up as a torque ripple. And similarly, when I want to de-energize, it will not happen also immediately. So this phase uh, current will still be there even though you don't want. So that may actually create problem because you are having current in the winding even in the zero slope region, or sometimes this current may be so large that it may enter even negative slope region. So if you want to, you don't want current in the winding, but still it is there because it is decaying slowly due to machine inductance. And since current is there in the negative slope region, if it is there, then it will develop a negative torque. So other phase will be giving positive torque. This phase which has to die down or remove the current from the winding is giving negative torque. So the net torque will reduce and your torque ripple will be higher. So this is the problem. So problem is ultimately during starting or ending. In the middle, there is no problem. Current, maintaining the current is not a big deal. Using hysteresis control or any control, I can maintain within the precise band. But starting, ending. So this ending is starting of another phase. So during switching of one phase to another phase only, there is a problem in the SRM, which can give a positive or negative torque ripple. So we designed one method to minimize the torque ripple in SRM drive so that SRMs become more commercially viable. So for that, we segregated or we divided the inductance profile into three regions. First one third part, second one third part, and third one third part. What are these? In the overlapping of four phases, if you observe here, the other phase is overlapping, other phase, third one third region is overlapping with this phase, and similarly this period only the blue phase is conducting, and this period there is again an overlap with the pink phase, right? So we only are seeing positive slope region because we are now interested in only motoring mode, right? So negative slope current should not be there and it should die down as quickly as possible. So if I off the winding at here, then we have to enter negative torque region because the winding current will never become zero immediately, even though switches I have turned off in the inverter or the converter. So the issue is I cannot switch off until I cannot wait until end to switch off. Otherwise, because I will enter negative torque region. And also there is another phase available in this period to have to contribute for the torque. So what we proposed is we switch off at this instant itself, where I reached only two thirds, one third, two third, three third. Right? After reaching two third, I will switch off so that current will slowly die down. It may not take as much time, but if it is taking time, there is sufficient time. It is not, I am not asking the winding current to go zero immediately here. I am off beforehand. Still, there is some positive slope region available for me to get the torque, but I am compromising. So if I off here, then it has sufficient time. So even though I have sufficient time, there is next phase coming. This phase, that blue phase, pink phase together will contribute. So then I have more torque than desired. That is also problematic because I want exactly the reference torque to be met. So then what we have done is this pink phase is at the lower inductance region and blue phase is at the higher inductance region. So higher inductance offers more resistance to change in current in comparison to lower inductance. So this blue phase, even though we switch off, it won't the current won't go zero immediately. So what we have done is this pink phase reference current, we try to adjust such that it gives only the remaining part of the torque after the blue phases torque. Why we are doing like that? So that net torque is still maintained constant approximately. And second thing is this current I have no control. I have given what all I can do and still there is current in this winding. Now, so what we do is we make the current in the pink phase, we start much before the zero slope region only or here. If what happens when I start beforehand, I have sufficient time to put current in the winding because removing the current or putting the current both will take time due to the winding inductance. So if I start early, by the time I reach here, I can have sufficient current in the winding, which I will have to control such that the torque produced by the pink winding is only compensating for the torque already given by the blue winding, right? So then what will happen is the net torque will become smaller or equal almost constant. So that is the objective. Objective is to have another phase also you check and then compensate for the loss, right? So ia star is iref minus ib square. So what happens is when I entered first one third region, ia first one third region is suppose here. So this reference is given based on this current, the remaining torque. If this current becomes zero, then I will give full reference to orange. And then this current will rise and give me the full torque that the motor is required to get. Right? And if it entered into the negative slope region, then negative torque also I have to compensate. So I have to generate more torque here. So this plus. So I reference will increase further. So we ensured that we maintain the square relation because the actual torque on the SRM winding is proportional to I square, not I. If it was I, we would have made it I ref minus I. But since it is I square, we try to maintain the square relation and keep the torque constant. Right? And once I enter third one third region, no need to worry because in the third one third region, is first one third region for the another phase. So that phase, if I am trying to compensate here, so then it will taken care of. This phase I need not do anything. The next phase, which it will be first one third part, there it will be trying to compensate such that torque is remaining constant. So this is the control block diagram of this algorithm where we are trying to control the SRM and based on the current references generated from previous phase winding. So we are sensing the speed and also reference current we are giving. There is a torque ripple and reference current algorithm which we have discussed. Based on the currents feedback, it will try to generate gate pulse to the asymmetrical converter. So this is the hardware prototype that we developed in the lab for the same setup, and these are the hardware results. So if you observe, every phase current is going slowly and coming also slowly, right? It will never be instantaneous. And there is a period where you maintain the current also, and this is the torque ripple. It reduced, but still it will be there because we cannot approximate much, right? So, but it reduced significantly, and this is the reference and actual currents if you observe. So, since the reference is on, so actual current is trying to track the reference. So when I said reference to zero, the actual didn't go to zero immediately. So it went slowly. So in this period also, the actual current will contribute to the torque and another phase also will contribute, whichever has entered the positive slope region. So because of that, you have small higher torque ripple, but this get reduced significantly if we calculated, it come out to be around 8%, whereas in literature, around 30-40% torque ripple is existing. Okay. So then we concentrated on the converter because control algorithm we got converter. For an induction motor, converter was straightforward. It is a three-phase inverter simply. But here it is a special kind of motor, and we also saw that you have to energize and de-energize every phase according to the inductance profile and cleverly do that, and how fast the current dies down or how far the current rises up, that will have a direct impact on the torque ripple. So how to choose a converter, and at the same time we have to maintain low cost also, so that we have at least one switch per phase only and not more than that. If you observe the converter that is designed in this hardware and the circuit, one phase, two switches, two switches, two switches, two switches. So total eight switches and eight diodes were used for this converter for four-phase SRM. If the phases increase, then again two switches per phase will increase. That will have a huge effect on the cost, because motor cost may be cheap, but converter cost will be higher, and so the drive cost will become higher, which we don't want, right? So we worked on something, and then literature also there are many converters that are proposed for SRM drives. Fundamentally, they are trying to complicate too much, and also limit. There is a limited demagnetizing or magnetizing voltage that can be obtained in the proposed converters. So you cannot apply any voltage as you desire in the proposed, in the available converters in literature. So this is a symmetrical converter which I just shown. It uses two switches per phase, applies plus VDC for energizing, applies minus VDC for de-energizing. So if VDC is 100, I can maximum apply plus VDC, maximum apply minus VDC only for energizing and de-energizing the winding, not beyond. So the slope of the rise of current or fall of current gets dictated or gets restricted with the DC link voltage. There are several converters proposed in literature having limitations, like they use huge number of switches, they use extra windings as well. They are specific for one type of SRM only, which is not generalized, and then they lack phase independence, because in convention in SRM all phases can be independent control. But if you make a converter which is dependent on phases, then this advantage will be lost, right? And then you need extra switches, higher ripple, higher switches again, fast demagnetizing voltage, not there, and also higher capacitor voltage ripple. So this reduces the life of the capacitor. So these are drawbacks existing in literature. Based on these, we proposed this converter as shown in the circuit diagram, where you can see L1, L2, L3, L4 are the windings of the SRM four phases, and we use only one switch per phase. Additionally, we need only one switch extra. So this we call it as N plus one switch converter for N phase SRM. So if phases are four, N is four, I need N plus one, five switches, right? So this way, as more phases increase, I have only one switch more than the number of phases, whereas asymmetrical converter we have seen two switches in one phase itself required. So if four phases, 4 into 2, 8 switches, whereas here only 5 switches are required. And diodes also only 4 plus 1, 5. So 5 diodes, so N plus 1 diodes, whereas in asymmetric converter you need double the number of phases, 4 phases, 8 diodes, 8 switches. Here 5 switches, 5 diodes. So component count reduced here, so the cost will reduce automatically. And along with that, you need one flyback inductor, that is, and one capacitor. Bus. That is the configuration of and connection diagram of the proposed converter. What is the advantage, disadvantage we are going to get? We'll try to understand from the modes of operation. So first mode is motoring mode. When I operate G1 for L1 phase, for L2 phase it will be G2, like that. So I am energizing the winding using VDC voltage, which is fixed. Energizing is fixed, and de-energizing directly through the capacitor. And this capacitor voltage I can maintain at any value. If it exceeds that value, then I operate the flyback switch G5 and then try to dump the energy back to the source. So I am regenerating the power and I am demagnetizing through capacitor, not through V. So in the capacitor, I can control in such a way that I can maintain minus 3V, minus 4V, minus 100V as well if I desire. So if 50 volt is charging the winding, with 500 volt I can discharge. What advantage that will give? That will give me fast demagnetizing, because more than magnetizing, demagnetizing winding is critical, because next phase will come into play. So the faster this goes out, the next phase can take over the torque. So demagnetizing voltage is completely under my control, and it has no restriction of value as an asymmetric converter, where only V can be applied maximum, not maximum, minimum. V only can be applied. Here any voltage I can control to be at CD capacitor, thereby I have more flexibility, and cost wise I am having lesser number of switches, so cost wise it is reduced drastically, and it will be further reduced as more number of phases will increase. Right? So this is the operating modes of control. To Because I have a reference current, so as until I reach the reference, G1 will be on. Once I reach the reference, mode 1 and 2, I will try to chop until, so that the current is maintained. When I want to completely decay, then I will to mode 2. Mode 2 is B, this mode 2. So I will only discharge the entire current in the winding and dump it into the capacitor CD. So when I dump the current in the capacitor CD, the capacitor will charge. When capacitor charges, I will keep one reference voltage for the capacitor. When it exceeds the reference, then I will give this energy back to the source by operating the flyback. Flyback mode 1, flyback mode 2. I give back the energy to the source. So, and maintain the required voltage at the capacitor. So this capacitor voltage can be any value as per my requirement, and that voltage will be maintained. So this is the control block diagram of this converter. We give a constant duty ratio gate pulses for dumping back the energy to the source whenever the capacitor voltage crosses a threshold. Until then, I will control the capacitor voltage. I will give this capacitor for discharging a particular winding, and for charging directly G1, G2, G3, G4 will charge the respective phases of the SRM. Okay. These are the simulation results, where if I maintain VCD at some value, it is able to track the VCD reference. It is here 48 volt, and then I change my VCD reference to 72 volt. Right. So this is the dynamics of VCD change. So linearly, I can change the capacitor voltage to any reference as I desire, and these are the currents flowing in the transformer IT1, IT2, flyback transformer, and this is the gate pulse G5, where I am trying to dump the energy back to the source. This is the SRM winding phase currents, and if I give a higher reference also, I am able to track torque ripple also as reduced, and this is the speed response. when speed change it because there is a torque increase. Right? So this is the hardware setup we developed in the lab. We use FPGA digital controller. This is the converter. This is also designed in the lab. So for VCD reference, change in VCD reference, we are able to track the VCD. And if you observe, higher VCD means more voltage I am applying for, more negative voltage I am applying for discharging the winding. So when I increase VCD, 0.6 millisecond discharge time became only 0.32 millisecond. Higher voltage if you apply, faster the winding will discharge. So it discharged faster. If I want more faster, I can increase my VCD reference more. It is independent of the DC link voltage. So I will get faster, more faster, maybe 0.1 millisecond. So I can decide how much discharge time I need. Based on that, I can also control VCD according to my requirement. This is the same whenever there is a change in the reference current, the torque also increased and speed also changed. So the normal operation is fine, and also I'm able to control the discharge time of the motor winding, which has a direct effect on the ripple, torque ripple. Right? So the torque ripple we are able to minimize. So this proposed converter, the novelty is it has almost half the number of switches plus one when compared to the conventional asymmetrical converter. It has variable voltage discharging capability with minimum voltage stress on the switches. Unlike another topology, C-dump converter used for SRMs, the capacitor requirement here is small, and also the flyback converter helps in regenerative action. Without dumping the energy somewhere, we are giving back to the source. Thereby, efficiency will be improved. And this converter has independent operation for all phases, and it can be extended any number of phases. Only one switch per phase extra you will be needing. So this we published in IEEE Transactions on Power Electronic recently. We applied a patent also for it. So this is about switch reluctance motor drives. So converters and torque ripple reduction. These are the two factors which need to be considered for SRM drive. And for induction motor drive, we have seen three control algorithms. Vector control giving the best performance, but it is complex. If you want only importance to performance, you can go for vector control. Whereas if you want to compromise little on performance, but still have a lesser complex algorithm, then you can go for direct torque control or VBF control. So EVs is the need of the hour. EV can be designed in several possible ways. We have seen choice of electrical machine and its control algorithm. Ultimately, making an electric drive for EV is a very important one of the main challenges of EVs. And machines free from permanent magnets like induction motor or switched reluctance motor are preferable for Indian context. Induction and switched reluctance motor are cheap and rugged, so hence they may be used for EVs. Different control strategies and research problems of induction motors and switched reluctance motors we have discussed. These are the references. Thank you. Yeah, if you have any questions, you can ask. Bhumaya. Yeah, so Mam Sharma has asked a question. Same DTC. DTC, there are many modified DTC versions that came. Some advanced DTC algorithm, which have more advantages in comparison to the one I discussed. So the recent latest one DTC can be used even for car drives.
Yeah, participants, if you have any doubts, I'm sorry, sir. Actually, my internet got cut. There was in the institute itself, there was some problem. So first,
No issue.
So participants, if you have any doubts, yeah, you can ask, sir.
Bhumaya Jula has raised hand. You have any question?
Sir, excuse me, sir.
Yeah.
Sir, we use batteries, so it is easy to use DC motors. Why will go for induction AC motors, sir?
DC motors,
Speed control
the
is also possible.
agreed. DC motors are not as rugged as induction motor because they have brushes, right? So brushes and commutator add uh, to the cost and also reduce the reliability of the DC motor. Same power rating DC motor and induction motor, if you see, induction motor looks less than half the size and weight, and it is more reliable because you have to use reliable, rugged, and also low cost motor for EV. Otherwise, the manufacturing cost of EV itself will go high.
Sir, for more conversion and inversion, more heat loss will be produced inside the vehicle.
Which
How to do it?
conversion?
For using more
Use the
converters,
converters. You have to use
Converters.
multiple
Yes,
converters.
more
yes, yes.
power loss will be dissipated in the form of heat.
Yeah. Thermal
For
management
reduce,
is an issue. It is an issue. It has to be hand and carefully designed. Whenever we design the converter, we see all possible worst case scenario and then check the thermal management. Heat sinks and other coolants must be designed according to the drive.
But I would also like to add up, sir, even for the DC motor also, there a DC to DC converter has to be used, I think. Without that, that's not possible, the required DC. So the
Yes.
converter,
Converter is a must because you have to change the voltage applied to the machine.
yeah, any other participant?
Bhumaya has raised hand.
I have one question.
Yes.
Uh, how is regenerative braking feasible in induction type motor?
Yes, it is possible. It is possible.
So that means we are operating the induction motor connected with some alternator, or the induction generator working as a motor.
No, actually, see, it is all based on slip actually. So you see, induction motor, see, regenerative braking is nothing but you are getting the power, right? You want to feed that power back to the grid. So when the vehicle goes through a slope, your speed automatically increases in the induction motor, right? But that is not according to the voltage that you have applied because you are not the vehicle itself is accelerating, right? Without giving any input. So in that scenario, you have to control the slip of the induction motor such that it will enter into the generating mode, and in generating mode you can take back the power. So converter also must be designed such that you have bidirectional facility, right? So you have to be able to pump power back to the source as well.
So it also requires some electric power requirement for the induction motor for generating the power.
No, you only operate the motor as a generator in that period where you are getting the higher mechanical input.
Okay, sir. Thank you.
Any other participants? If you have any doubts, you can ask. I have one question. When charging any electromobility, the transformer have. So did you see the chat? Because the chat is.
I can see. When charging any electric mobility, the transformer have harmonics. So any method to reduce the harmonics. So that is a separately has to be tackled at the transformer level. Some filtering or some filters, active or passive filters, have to be used there to reduce the harmonics. But these converters, when we connect to the transformer, they will definitely draw harmonics. Yeah, LCL filter or any filter has to be designed. There are some active filters also. LCL filter is passive filter. Some active filter also can be there, which with switches.
Hello, good afternoon, sir.
Good afternoon.
So actually, I messaged you. So I applied so LCL filter for the same. So any active filters? Will you please name any active filters?
You just search by the word shunt active power filter. You will get a number of literature available in IEEE Explore. Okay.
Okay. Okay, sir. Thank you, sir.
Yeah, Indian road condition, which motor will be efficient. Uh, efficiency not only road condition, how we operate the vehicle also will make a matters on the efficiency. So all motors available above, you can operate above 80% efficiency, unlike you can get above 80% efficiency, which motor means almost all are similar, unless you go for permanent magnet based motors. Permanent magnet motors will give above 90% efficiency because of the reason that flux need not be produced separately, right? So you need there the core loss and other things will go. So, but non-permanent magnet based motors above 80-85% easily is achievable, right? And how much you actually achieve depends on the road or and also on the way the vehicle is driven.
Participants, anyone else want to ask any doubts to sir? So I think we can wind off. And I first of all thanks sir for this wonderful session. And that shows like how people were listening. So many had doubts to us, later projects on working with. Sir, any latest project you are working on? So one of the participants want to know like what is the latest project on which
Yeah,
you are.
this switched reluctance motor work which I have shown today is the latest work. All the papers 2022 are published. So we are trying to extend this further to have some advantage, some more advantage on the switched reluctance motor drive.
So then, like nowadays, is switch reluctance motor like in market in any of the vehicles?
Yeah, some have come in foreign. In India also, I've seen one or two. I think they are coming up because of the main drawback of torque ripple and converter. They are little lagging now. Which many algorithms have been published. We have also published. So I think with this, the problem issue is more or less
So,
sorted.
because I was just reading an article and there Tesla is using induction motor only for their
Yes,
vehicles.
yes, cost because of cost.
Cost. Yeah. Yeah, participants, I thanks sir for this wonderful session and like for any time when we call, sir has never said no. So thank you, sir. Thanks for joining with us and giving this wonderful lecture. And we like require more support from you in the future courses also.
Sure, sure.
Yes, sir.
Thank you very much.
And participants, with this session, with this we end this session, and tomorrow at sharp 9:30 we will have the next session. So we will meet at 9:30. Thank you. And for the materials, I'm just collecting it. So we will try to say, get all the materials, and by tomorrow we will be sending it. Okay, so you will all get the materials by tomorrow.